Hi folks, welcome to day 18. Today we're going to be beginning chapter 8, which is all on the function y equals ax squared. So before we get in to chapter 8, I first off wanted to congratulate all of you for making it through chapter 7. I know that that's really tough to do online, and I'm super proud of all of you for being able to do that. So let's go ahead and dive in. So you can see I already have some things written on the screen because I have a few pieces of vocabulary that I wanted to introduce today. So that way when we're using them throughout the rest of this week, you can know what they mean. Also, something that's really important is that on Friday, there will be no quiz. No quiz on Friday because you have a test this week. I want to try and be reasonable with y'all. So no quiz on Friday this week. Alright, let's go ahead and jump into some vocab. So the first vocab term I have for you is something called a vertex. Now, a vertex is the point on a graph where the function changes direction. So if I'm looking at my graph here, which is of y equals ax squared, you can see that it's moving down, it reaches a point, and then it starts moving up, right? So this point here where it changes that direction, that is what we call the vertex. So this center point here is our vertex. Now, it's not always going to be at the exact, what is called the origin, right? It's not always going to be on the origin. It's going to move around because we are going to be moving our graph around. All right, but I just want you to be able to identify where it is at this point on a graph. So you can see it's the point where it changes direction. It was going down, then it's going back up. The other way to think of it is a vertex is always either a peak, meaning it's the top of like a hill, or it's a valley. So it's the bottom of the hill, right? Or like the bottom of two hills, right? So it's a vertex is either a peak or a valley. So peak, meaning it's like uphill, or valley, meaning it's at the base. All right? Axis of symmetry. So the axis of symmetry is an imaginary line that splits a function into two symmetric parts. Symmetric just means that they're identical and they're mirrored. And I'll let you know your axis of symmetry is always at the x value of the vertex. So we're going to start with our example here with identifying the vertex. So you can see we're going down, hit the bottom of the valley, and then we start going back up. So that center point in that middle there, that's going to be our vertex. And since that's the vertex, we know that if we make a dotted line going up and down at that x value, that is our axis of symmetry. All right, AOS, axis of symmetry. This pink dotted line here. I'll go ahead and I'll draw in purple like a full line for you to see. So that would be roughly our axis of symmetry. You can see I'm not drawing these perfectly because I'm not on like grid paper, but that's okay. All right, so that's the axis of symmetry. The next two pieces are really important pieces that you're going to see throughout all of your math like years, and those are domain and range. Domain are the x values of your function, and range are the y values of your function. All right, so for our function for any quadratic, right? This is a really terrible graph of a quadratic, but that's okay. For any quadratic, anything whose leading coefficient or leading power is an x squared, all right? Anything that looks like this, then we know that the domain, the x values, you can see if I'm looking for the value of the function at this, I don't know, maybe this is like 2. Right, all we have to do is go up, see where it hits the function, and then go to that y value. So that's the x, this is the y. We can do that over and over again with any x any x value we want. So we can go over to 4. If my screen allowed me to, I could go all the way over to like positive 100 or all the way over here, right? So you can see like our graph doesn't extend this far, but I could look all the way over here and I could trace out where this is kind of going. We don't do that because, you know, there's arrows for a reason, because we have a finite amount of space, but that's how you could do that. So you see that the domain, if you're looking for any x values, it doesn't matter where you're going, what x value you're looking for, you're always going to hit the function somewhere. So I could go over here at -3, I could see if it hits the function. If I go up, I see, oh yeah, it hits the function at some y value. All right, so that's all that domain says. This domain here of all real numbers, this little r thing, that just says, hey, when you're going through and trying these problems, when you are graphing them, does every x input have a y? And the answer is yes. That makes sense. All right, and let's talk about that real quick. Every x value has a y. So if you have ax squared plus bx plus c, all right, that's your function. That means you can plug in x equals 1, you can plug in x equals 2, you can plug in x equals 0, you can plug in x equals 500, right? And as long as you have values for a, b, and c, right, as long as those are numbers, then you'll get an x value out. So for all quadratics, the domain is always all real numbers. All right, so that little r that you see, the double-lined r, means all real numbers. Range is really, really similar. Range is the y values of a function. So just like when I said, oh, you know, sometimes we're going through and we're trying to find the x values, you can see that it exists, our function exists for all x. But if you're looking at it, right, if this is our function, there are some places that doesn't have a y. So anything underneath your x, so anytime that y is less than, or anytime that you're looking at y's, when your y is less than 0, you have nothing down there. So your range, where your function exists for any positive a, which looks like this little function I have up here. For a positive a, so a bigger than 0, you have nothing going on underneath your x-axis, which means your function, your range, is that y, for any time that a is bigger than 0, y is bigger than or equal to your c value. All right? Similarly, for when a is less than 0, it's going to look something like that, and you'll learn about that more tomorrow. But then we'd say y is less than or equal to c. If we're just looking at the basis of like ax squared, when a is bigger than 0, it's going to look like this. So that means that you can see the only place that my function exists is above the x-axis. So we say that for this, our range is that y is bigger than or equal to, instead of c, right up here we had c, my c now, I don't have 1, my c is 0. So since my c is 0, I say y is greater than or equal to 0. And similarly, I don't have a c value for my other example, when a is less than 0. So when a is less than 0, your function is gonna look something like this. So we say, again, it's just like up here, right? If a is less than 0, then y is less than or equal to c. But my c value, there isn't one, so my c value is 0. All right, let's go ahead and recap that. Vertex is the center point, right? The place where your function's changing direction, and it's either going to be at the top of a peak or at the bottom of a valley. Your axis of symmetry is the imaginary line that splits your function exactly in half into two symmetric equal pieces, and the axis of symmetry is always at the x value of your vertex, which we'll get into tomorrow. Your domain is always your x value, so your domain for quadratics is always all real numbers. And your range is the y values, which depend on what is going on with your a. When a is bigger than 0 and you have a c value, then your range is y is bigger than or equal to c. If a is less than 0, then you say y is less than or equal to c. If we're dealing with a more basic function, though, where you don't have a c value, then if a is bigger than 0, we say y is bigger than or equal to 0 for your range. For a is less than 0, we say that y is less than or equal to 0 for your range. All right, now let's go ahead and use some of these in an example. All right, because that was a lot of information, but it doesn't really do us much if we don't try out in examples. So what we're going to do is we're going to evaluate the function y equals negative 3x squared. All right, we're going to evaluate this, and we're going to describe the domain and range. So when it says to evaluate it, it just means, hey, plug in some numbers for x. Now, for the purpose of this course, the numbers you're going to pick for your evaluation piece, the numbers for x you're going to plug in are negative 3, negative 2, negative 1, 0, 1, and 2. The reason why you're picking those numbers is they're all relatively small, and they have numbers that are positive, right? So we want to see stuff going on over here, and we want to see what's going on over there too when we're graphing it. We're not going to be graphing these today. We're just making t-charts and describing domain and range today. We'll be practicing graphing tomorrow. So when it says to evaluate, we have different values for x. So what we're going to do is we're going to go ahead and plug them into our equation. So we have y equals negative 3 times x squared. But my x is now negative 3. So I have y equals negative 3 times x squared, but x is now negative 3. So I'm going to put that in parentheses so that way I know that I have to square my negative 3. So the negative is also squared. This is really important because negative 3 squared, right, is different than negative and then 3 squared. So if the negative's on the outside, then your answer is negative. If the negative's on the inside, then your answer is positive. So that's why it's really important here. All right. So now I have my problem set up. I plugged in my x. I plugged in my value of x. All right. Where you're going to mess up, because inevitably students do mess up, and when they mess up because they forget about PEMDAS. PEMDAS says, hey, there's an order that we have to do things. First we deal with parentheses, then we deal with exponents. After exponents, we do multiplication or division next, depending on, we either do multiplication or division, depending on which one comes first when we're reading our problem left to right. And then we do addition and subtraction. And again, addition and subtraction can happen in the same step, depends on which one comes first when reading the problem left to right. But you always start with working with your parentheses and your exponents first. Then you move on to the multiplication division piece. All right? So my first step is going to be getting rid of my exponent. I'm going to get rid of my exponent by squaring that negative 3. So, since we have negative 3x squared, we have negative 3 times x, but x is now negative 3, so we have negative 3 squared. Negative 3 squared is just negative 3 times negative 3, which is just 9. Now that we've gotten rid of this exponent, all right, now that exponent's not there, now it can multiply. So we have negative 3 times 9 gets us negative 27. Now we're going to do the exact same process for our other values of x. So we have negative 2 squared times negative 3. So negative 2 squared gets us 4. 4 times negative 3 gets us negative 12. Going to do that same thing with that negative 1. So you have negative 3 times negative 1 squared. Negative 1 squared is positive 1. So you have negative 3 times positive 1, just gets you negative 3. So we have negative 3 times 0 squared. And again, all I'm doing is instead of drawing in this x, I'm plugging in these values, all right? So 0 squared is just 0. 3 times 0 is 0. And we have negative 3 times 1 squared. 1 squared is 1. 1 times negative 3 is negative 3. Last but not least, we have negative 3 times 2 squared. 2 squared is 4, so we have negative 3 times 4. Negative 3 times 4 is negative 12. All right, so we evaluated it. Again, evaluating just means making a T-chart. The reason why you're going to want to put it in T-chart form is because this is going to help you for tomorrow for when we're actually graphing. So I strongly recommend putting this in T-chart form. All right, then we're going to go ahead and describe the domain and range. So for your domain, with the domain, we know that for all quadratics, the domain is all real numbers. So that's all we have to put for our domain. That's it. That's our answer. X is all real numbers, or X equals the double-lined R. So that's your domain for every single quadratic problem. So I don't want anyone to be like, wait, Miss Kessler, I didn't know what domain was for a quadratic, because the domain for a quadratic for every single one is all real numbers. Your range is your y values. And again, that depends on your a. So RA, right, we have y is equal to a x squared. RA is negative 3. So I'm going to write myself a little note. A is equal to negative 3, so A is less than 0. I then go back up to my notes, and anytime that A is less than 0, and I have a function of the form ax squared, my range is that y is less than or equal to 0. So my range, I just write, is y is less than or equal to 0. All right, so all we had to do for the range was go back and look at our notes. All we had to do for the domain was go back and look at our notes. Your domain for every single quadratic is all real numbers, and your range just depends on that a value. All right, it depends on the a value and whether or not you have a c. So in this case, since we just had a basic negative 3x squared, it was really basic, so we had a super basic range. What I'm going to have you do for your practice problems is you're going to do 4 more that are very, very similar to this. I also have 3 other examples in the written notes, which are different from these examples, or from this example. So if you got stuck, you're welcome to read through the written notes. I just didn't want to elongate this video any more than it needed to be. All right, so go ahead, try out those example problems. Make sure that when you're doing that, you're making this T-chart. And when it asks you to evaluate from x equals negative 3 to x equals positive 3, that just means what you're doing here. All right? That's all I got for you today. Thanks so much for watching.